Okay, awesome. So again, my name is Charles, and I'm from the Michigan Science Center. What I do for the Science Center is I get to travel. So I do all of our traveling science programs. I get to go up to the Upper Peninsula and spend a week there camping. It was awesome, trust me. And we saw over 10 libraries up there where we did similar programs. And we're afforded to be able to do these programs thanks to the Community Foundation for Southeast Michigan, which sponsored over 25 programs in the Southeast Michigan area. So we would absolutely like to thank them if we could give them a quick round of applause as well. Thank you so much. So this year's reading theme is Fizz Boom Read, and so the Michigan Science Center thought, well, how awesome that we can bring science to the community, and by giving you Fizz Bang traveling science. So today we're going to be talking about combustion, and we're going to be learning about explosions as well. And I know you guys are really excited. All right, but I'm going to let you know which things you can try at home and which you should absolutely not try at home. All right, so a couple things to note first. Up here you will see some safety equipment. I'm going to go ahead and throw on some gloves because there are certain things that I'm going to be touching today that I don't want touching my skin. So gloves are extremely important. I also have a heavier pair of leather gloves that I'm going to be putting on a little bit later for another demonstration. What other safety things do you notice that might be up here? Go ahead and just shout them out. Oh, the fire extinguisher. Yes, absolutely. Now, fortunately, we've never had to use the fire extinguisher. I don't plan on using it today either, unless it's absolutely necessary. And I'd like to kick things off with an explosion straight away. Who wants to help me out with that? I need 2 helpers for this one. I'll take you right there in the tie-dye, and I'll take this guy in the black shirt right there. Yeah, come on up. Let's give them a big round of applause. All right, so remember how important I said safety is? You guys are both going to put on your safety goggles. Thank you so much. And I want you to step up to right about here. Come on over here, and then wave goodbye. I'm just kidding, I'm kidding. Okay, so I've got 2 things for you. I need you both to hang on to those. These are graduated cylinders that we're going to use as a launch device. All right, so we're going to create an explosion down inside of this chamber here, okay? And the way that we're going to create that explosion is with the use of this antique device right here called a film canister. Does anybody remember film? A couple of us, yes, okay. So this is one of those things that you can try at home if you have access to these. So we're going to add a little bit of water to our film canister. And in fact, I've got another one here. We'll pop the lid off there. A little bit of water. Now we know that water isn't very reactive, is it? No, it typically doesn't react with much. But what will react is Alka-Seltzer. So we're going to drop some Alka-Seltzer inside this water. Now, if you've never used Alka-Seltzer before as a kind of medicine, you've probably made a volcano with baking soda and vinegar. Who's done that? Yeah, lots of hands there. So baking soda and vinegar, when you combine those 2 ingredients, they bubble and they fizz and they create through a chemical reaction carbon dioxide gas. All right? So this is going to do the same thing. When we drop this inside the water, the 2 ingredients will mix, will create carbon dioxide gas, but inside of a sealed container. Now, if you guys are familiar with balloons, if you put too much air inside of a balloon, what happens? Yes, it absolutely pops. So here's the thing. Where are we going to launch our canisters? How about you hold yours out that way, all right, excellent, and you hold yours out that way. Now, we're not pointing it right at anybody. It'll certainly fall before it hits anybody, all right? But keep an eye out, kind of like when you're at a baseball game, okay? We're going to drop a piece of Alka-Seltzer inside here, close that up, slide that in there, and just wait real quick. I've got another piece here. And inside, the creation of that gas is building up the pressure. So the pressure is getting higher and higher and higher, just like blowing up a balloon. The gas is being created, filling up the canister. Eventually, it's going to be too much for the canister to handle, and we should get a pop. But we never know exactly when. It's always kind of timed differently. Her piece was, oh! That was perfect. That was perfect. So I'll take your safety goggles, guys. I'll take your safety goggles from you. Let's give another big round of applause to these guys here. Thank you both so much. You guys can head back to your seats. All right, so we created an explosion inside there. So what I'd like to do is to remind you guys of the states of matter. So who can give me a state of matter? Yes, solids. So we have solids. What's the next one? Liquids, and then there's one more. Gas. There's also one called plasma, but that's another show, okay? So we're going to talk about solids, liquids, and gases. Now, the molecules in each one of these states behave differently, okay? So the molecules that build up all things, you're made of molecules, the floor is made of molecules. The molecules inside of a solid are very, very close together. Very close together, and they're just kind of shaking a little bit. They're kind of vibrating, all right? But if we add a little bit of energy to that, and those molecules start to add energy into themselves, they start to move around a little bit more, and that's where we get liquids. So liquids take up a little bit more space because those molecules have more energy, they're moving around. But how about gases? If we take a pot of water, we put it on the stove, what happens to it? It starts to boil, and then it starts to evaporate, right? So boiling is the process, evaporation as it heads up into the air, changing from a liquid into a gas, the gas form of water, of course, water vapor. So gases take up a lot of space. So the creation of the carbon dioxide gas inside the film canister took up so much space that it pushed out the bottom of the cap, and which way did that canister go? We went out, right? So just like a balloon, if you were to blow up a balloon, let it go, it would just take off into the audience. Pretty cool, huh? Now, we can sort of relate this to rockets as well. But what comes out of the bottom of a rocket? Oh, fire. So should we go to the fire part? Okay, I want everybody to raise your hand. Say I. State your name. Promise to never, ever, ever try any of these things at home. So as I said, a lot of these demonstrations could be very dangerous, but I know how to keep myself safe, how to keep you guys safe as well. So what I have right here is an old water jug. And to this water jug, I'm going to add a liquid, okay? This liquid is quite flammable. So I'm going to add some inside here, just like so. Then I'm going to start to swirl this liquid around inside of the canister. And what do you think is going to begin to happen to it? As I start to coat the inside, it starts to evaporate. Remember what that means? So it's changing to a gas. So as we swirl this around inside, it's coating the walls, it's beginning to evaporate. I'm going to drain out the excess liquid into our jar right here. And then, what do you say we light it on fire? That sounds pretty cool. Now, typically, when fire comes out of the bottom, the rocket goes up, all right? We're going to do it backwards. This is an upside-down rocket, all right? So we're going to put this one like that. We should see quite a bit of fire come out of the top here. It might happen very, very quickly as well. So you may wish to cover your ears if you're sensitive to loud noises. Are you ready? Should we count down? 99, 98. All right, 3, 2, 1. Pretty cool, huh? So we ignited that flammable gas and that flammable liquid that started to evaporate inside there by adding some energy to it in the form of heat, right? That's what that lighter gave us. It gave us some heat. And as those molecules increased with energy, they started to take up more space. And which way did they go? Out the top of the bottle, right? So they all had to leave the top of the bottle. We created thrust. If we did it on its side, which way would the bottle go? It would go that way as all of the flame would shoot out that way. All right, so once again, please do not try this at home. It's very, very, very dangerous, okay? So before we continue with our explosions, I want to talk about combustion. Combustion is really just a fancy word for fire. So a combustion reaction is a chemical reaction that involves three things, three important ingredients. And I'd like to ask you guys what you think those ingredients are. So let me set you up for the example. Say you're building a campfire. What are some things that you need for your campfire? Yes. We need wood, absolutely. And wood is a good what? It's a good fuel. Yeah, absolutely. And so we'll talk more about fuel in a second. What else do you need? We need oxygen. Excellent answer. We definitely need oxygen to help with that reaction. And then we need one more thing. What is that? We need fire, which provides heat. Right, absolutely. So you guys are good. 1, 2, 3. Got them. So we need fuel, we need heat, and we need oxygen. So let's examine each one of those ingredients a little bit more closely. Okay, so let's start with fuel. Now, what could we use as fuel? We know that we can use wood as fuel. We know that we could use gas in the form of natural gas. Actually, that's how we got here today. Our van is powered by natural gas. Coal could certainly be used as a fuel. What else? What else? Paper could be used as fuel. Sure. What else? Yeah. Coal. What do you think? Yeah. Metal. Oh, I like that one. So if I were to take these tongs right here and light these on fire, do you think they would burn very well? Probably not. However, if metal is involved with some other chemicals, maybe it would burn that way. So you guys know that stuff that you shake onto your French fries? What is that? Salt. Does anybody know the chemical formula for salt? What do you think it is? Minerals? We're almost there. What do you think? Sodium what? Sodium chloride. So sodium chloride is a metal salt because sodium is a kind of metal itself, okay? So sodium chloride is a kind of metal, so maybe we could burn salt. But maybe we have to dissolve that salt first. So to be able to do this, we have a butane torch here. So butane is another kind of fuel. And I'm going to turn this on here and ignite this. And we've got a nice blue flame right there. So as I'm letting that warm up, I'm going to show you these 3 bottles. Inside each one of these bottles is a different metal salt. So this first metal salt is strontium chloride. So strontium is a type of metal that we don't often see or hear about, but this is the metal salt dissolved in a solution of another flammable liquid. So if we spray this liquid through our flame here, I want you to see what properties it has when it burns. Are you guys ready for this? This is pretty cool too, all right? It's not loud, so you don't have to worry. Here is strontium chloride. What do you think about that? All right, so what color was that? Yeah, nice red flame. So we know that strontium burns red. Okay, let's take our lithium chloride. So lithium, another kind of metal. This is our metal salt dissolved. And let's see what color this one burns. Are you ready? Here we go. Oh, that one's pretty neat too, isn't it? And we get a little smoke from that one too. Okay, so that's lithium chloride. So strontium we know burns red. Lithium burns that nice pink or magenta. And then we come to copper. So who's familiar with copper? Yeah, copper's in wires. Copper's on the outside of pennies. It makes our pipes. All right, so this is copper chloride dissolved into solution. Are you guys ready for this one? Any guesses as to what color this one might be? I'm hearing a lot of green. Are you guys telling me I need to change the color of my bottles? Okay. So here we go. Here is copper chloride. That one's pretty cool. So we now know that metals can indeed burn. Metals can be used as a fuel. So where have you seen different metals burning? And remember those different colors. Where have you seen this practice before? What do you think back there? Fireworks, absolutely. So I know that some of you probably just forgot about all the fireworks that you saw, or you're maybe still seeing. But there's different metals inside those fireworks. So as those firework bombs go off, those metals inside there are burning. So in a green firework, there's a chance you could see copper burning. In a magenta firework, maybe lithium. Or how about a bright white firework? You might see aluminum or magnesium. Or maybe inside of a yellow firework is sodium. So sodium chloride, just like the salt that you put on your foods, burns bright yellow. Okay, so we know that metal can be used as a fuel. I was thinking for this next one, I could use a little help. And, well, here's what I really need. Here's what I really need. And this is always a little awkward for me. I need some money. Yeah, I need some money. Particularly the rectangle kind. The bigger the number, the better. The bigger the number, the better. So let's see. We've got some money. Here we go. Here's some money. Batman's going to pay me. Come on up here. Ooh, a 20. Nice. Okay, who else has money? No, I'm just kidding. I'm kidding. All right, you can stand right over here, all right? Stand right over here. So $20. This is pretty cool. I didn't think we were going to get this. So a $20 bill. Can anybody tell me what this is made of? Yeah, we often call it paper, but is it really paper? Linen. So it's actually made of cotton. So very similar to what your clothes are made of. It's made of cotton. So what was your name again? Preston. So Preston gave me $20 to use as a fuel. That's pretty cool, isn't it? All right. Let's see. You know what I was thinking, though? Maybe 2 fuels would be even better than 1, don't you think? 2 fuels better than 1. So I've got remember all that excess fuel I poured off of the container? I got it inside here, and I'm just going to go ahead and soak this in there if you don't mind, all right? So we're going to soak our $20 bill inside of our fuel. There we go. Excellent. You know, the Michigan Science Center is a nonprofit, so I would like to thank you for your donation. All right. So there we have our $20 bill soaked in our alcohol. All right, and then we're going to light it on fire. All right, Preston. Here we go. Thank you so much. Here we go. 3, 2. Hold on, I gotta get my lighter. There we go. Very nice. Excellent. But wait. Okay, we'll try it again. Here we go. All right, soaking it once again. No, this is gonna be good. It's gonna be really good. Preston, that was cool, wasn't it? That was pretty cool. Okay, so here we go once more. In 3, 2, 1. Excellent. There we go. And, oh. All right, okay. So I realize that I can't actually burn Preston's money, right? So we'll go ahead and dry this off for you. And now, you notice that I'm drying it, right? Because there was something else inside that fuel. What makes things wet? Water. So there was water inside there. So as soon as I added this bill into that fuel mixed with water, the bill absorbed a lot of that water. Now let me ask you this. When you take a pot of water and you put it on the stove to boil it, does it happen really fast? No, it takes a while, right? Because it takes a lot of energy to increase the temperature of that water. Now our alcohol that was in there as our fuel burned very, very quickly, and it couldn't raise the temperature of the bill high enough for this to burn, all right? Which is good news for Preston. So I'm going to give this back to you and say thank you very much. Round of applause for him. Now I can almost guarantee that that's the cleanest money Preston's ever held too. Okay, so that brings us to heat, right? That bill could not get hot enough to burn. Couldn't get hot enough. So what are some ways that we could generate heat? What are some ways that we can generate heat? I'm looking over here this time. I see the same 2 hands. What do you think? Yeah. A match. And how do we light a match? How do we light a match? Yeah. We light a match with fire. You could light it with a lighter. What do you think? Oh, he said the word. And that's friction. Friction. So I want everyone to put your hands together and start rubbing. What's starting to happen? It's getting hot. Now hold on, stop. I don't want anyone to catch on fire. No, I'm teasing. That won't happen. But friction opposes motion. So friction can create heat. Now, just like when we rub our hands together, you could rub 2 sticks together to create heat, and that's how we started early fires. You could also slam 2 rocks together, and that would create some heat. So let's try this. I need another helper for this one. And I was thinking that, how about you in the blue back there? That's you. Yeah, come on up here. Come on up here. A big round of applause for her as well. And I have a pair of safety goggles for you. Okay, turn and face everybody. Wave goodbye. I'm just teasing. It never gets old, though. Okay, so what we're going to do is I'm going to have you hold on to this with my pair of tongs. So go ahead and hang on to that. And just hold on to this piece of paper. We're going to see if we can burn this piece of paper with the use of these two spheres, these two steel spheres. So just by slamming these together, we can create heat. But the heat is created right at the point where they touch. And it's a very, very small space. So right where they touch, we can create some heat. So we're going to see if we can burn this paper with friction. You guys ready for this? All right, here we go. In 3, 2, 1. Now hold on. Give that a smell. What happened? It smells like smoke. It smells like smoke because we actually burned some holes right into our card here. So right at the point of contact where those two spheres collided, it got extremely hot and this paper was used as fuel. But we couldn't heat the surrounding edges of the paper because only at that point did it get hot enough to burn. So pretty cool, isn't it? So I'm going to give that to you, and I'll take the safety goggles. Thank you so much. Another round of applause for her as well. Now, I was thinking that these are kind of small, don't you think? So maybe if we scale up the size of these spheres, we can get a better reaction. You think? All right. So I've got two spheres inside this box right here, and they're much larger. So in case you're wondering, this is where I get my workout every day. All right, is lifting these guys. So you'll notice that they look a little bit different, but underneath the aluminum foil that this one is wrapped in, it is exactly the same. These are made of iron. And what do we know about iron when we leave it outside, sometimes in the rain? It starts to get rusty, right? So both of these spheres are covered in iron oxide. So oxygen reacted with the iron, creating the rust that we see on the outside of these spheres. Now, one of these spheres is wrapped in aluminum foil. And the reason being is because when we slam these two together, it's going to get very, very, very hot. All right? And when it gets hot, the reaction will be that the aluminum is going to steal away the oxygen from the iron oxide and create aluminum oxide and leave behind elemental iron, okay? This one could be a little loud. I never quite know. So I'm going to go ahead and cover up my ears with these. But here's the deal. When I start slamming these together, I'm going to try it a bunch of times. So keep your ears covered until I take mine off, okay? Because sometimes I just have to rotate them to get it to work really well. Are you guys ready for this? All right, here we go. Go like this. All right, here we go. In 3, 2, 1. Pretty cool? So once again, we know now that oxygen is extremely important to these kinds of reactions. So what you guys actually just witnessed, I'm sure you've witnessed before, but in a little bit different way. Who here has used a sparkler before? Okay, cool, I thought so. So sparklers work very similarly where you have a metal oxide and another kind of metal that under intense heat will throw out sparks and all kinds of light as well. So we've released energy in a couple different ways. We heard some sound, we saw some light, and there was also lots and lots of heat energy because those sparks were intensely hot, okay? And that's why we want to make sure that when you're using sparklers, those 3,000 degree sticks of metal that we hand to you, that you're extremely careful, okay, because they can be extremely dangerous. So now we know that oxygen is very important, so that brings us to that third ingredient. And to talk about oxygen, I have a kind of liquid here that I think is pretty unusual. So the liquid that I have here is hydrogen peroxide. Now, who's heard of hydrogen peroxide before? Okay, so hydrogen peroxide, the stuff that you guys buy in the store for first aid, is about 3%. 3% hydrogen peroxide. The stuff that I have inside this bottle here is 35%. So this is a much higher concentration of peroxide. So what hydrogen peroxide is a liquid that contains a lot of oxygen. So you might know that water is H2O, right? That means there's 2 hydrogen atoms and 1 oxygen atom. All right, this is H2O2. So this contains some extra oxygen. Now, there's a really cool reaction that, believe it or not, is happening right now. I know, it's not very exciting. The reaction is actually that this is decomposing. So the oxygen is leaving the liquid and leaving behind water. So if you've ever bought hydrogen peroxide, you know that it's stored in a brown bottle because light will increase the rate of that reaction. Well, there's another thing that will increase the rate of that reaction, and it's called a catalyst. And so I've put some inside of a piece of paper here. It's a very fine powder. When I add this to our hydrogen peroxide, the rate of the reaction will increase very, very rapidly, and it will begin to release all of that oxygen that is kept inside that liquid. So here's what's really cool. I'm going to light this stick on fire, all right? And as this burns and releases that extra oxygen, I'm going to blow out that stick so it's just glowing on the end. You've all seen a stick glow because it's very, very hot. I'm then going to stick that stick back inside here and see if we can get it to relight. All right? Everybody cross your fingers that this works because it doesn't always work, okay? I always say that, that if it moves, it's biology. If it stinks, it's chemistry. And if it doesn't work, it's physics, right? So there's always a chance that it will not work, but that's the great thing about science is that there's a reason why it doesn't work, so we can go back and investigate why. Okay, are you ready? All right, so I'm adding our catalyst. Here we go. 3, 2, 1. And lots of oxygen there being released. I'm going to go ahead and ignite our stick here. Just like so. Just so we're glowing on the edge there. It's a little stinky. All right, and I'm going to go ahead and blow that out just like so. And you see that it's glowing on the edge there. Let's try it if we place it just like so. You can see it's glowing a little bit brighter. It's glowing a little brighter. Unfortunately, it didn't work for us. But what we did see was a large cloud come out of there, and it came out of there quite fast, didn't it? So the cloud that you guys actually saw was condensed water vapor. It was, in fact, a cloud. The oxygen gas that's being released from there is a clear and colorless gas, so you can't actually see that. All of the black stuff that you see at the bottom there is the powder being mixed with the liquid that's now still inside the container, and that bottle being held up by that clamp there because that reaction was very, very hot and shrunk the plastic. Now, why is something like this useful? Has anybody ever seen a jetpack? The guy presses the buttons and he takes off into the air with the pack on his back. Yeah, so typically they use hydrogen peroxide for that. So hydrogen peroxide is pushed out through a couple channels into a catalyst, and all of that oxygen is released, but it's pushing down, right? So then our person with the jetpack takes off up into the air. Okay, so it's pretty cool. All right, so we're going to go ahead and set that one aside. I'm sorry that our stick there didn't reignite for you. Our oxygen must have not been in the right concentration. All right, but what I'd like to do for you now is burn something else. All right, some more fire for you. And what I've got here inside this bottle is a very, very fine powder. And I'm going to add a little bit of that powder to our watch glass here. So you can see that it's a very fine, kind of a yellow powder. Everybody see that? Okay. It is highly, highly flammable. Okay, so what I'm going to do is burn it all right? And, of course, taking all safety precautions. Okay, are you ready? Whew. Here we go. In 3, 2, 1. Okay, that's 2 failed experiments. No, I'm just kidding. No, actually, it did work. It worked. So if you look closely, what happened to the powder? It burned. It burned on the top. You can see that some of it is brown on top there. So it definitely did burn. But hold on. Hold on. What was that third ingredient that we said was ever so important? What was it? Starts with an O. Oxygen, right? That third ingredient is extremely important. So when you guys build your campfire, do you start with a huge, giant log? No, what do you start with? Sticks, paper, leaves, twigs, things like that. Really, really small pieces of wood because we're increasing the surface area. So oxygen can get around all of those parts and help things burn. So this powder is so fine. It's so fine that it's all sitting on top of itself really well, and oxygen can't get around the inside of all of that powder. So it would be like taking a big log right here and trying to light the whole thing on fire with one tiny little flame on top. Not going to happen, right? So the way that we're going to burn this is by mixing it with the air, like that. All right? This gets really, really cool. Okay, so what I've got here is a small launch device with a tube attached to it. And I'm going to add some of our powder into our tube, just like so. So what do you think that I might be doing right here? What do you think I'm going to do? Yeah, we're going to blow some air through this tube. We're going to blow all of this powder into the flame at the end of the lighter, and we should get a pretty nice fireball. You guys ready for this? Okay. Here we go. In 3, 2, 1. Well, again? One more time. Okay. So, here we go again, our famous fireball. In 3. So just by mixing that powder with the oxygen, or just by spraying it through the air like so, we're able to get a pretty good flame from there. All right, here we go. If I can get my lighter to light. Is that awesome or what? So we know that fuel is extremely important, and we know that our lycopodium powder here, a powder that is derived from a club moss, is extremely important. We know that heat is important. We got that from the flame that was created from the lighter. And we know that oxygen is important. And where did we get our oxygen for that demonstration? It's in the air, right? So we breathe in the oxygen, we exhale the carbon dioxide. So oxygen, extremely important. Now, this wouldn't be an explosion show without one really good bang at the end, right? So all of those demonstrations I think were cool, but we need something big, don't we? Yeah, I agree. So here's what we're going to do. We're going to combine all of our knowledge from what we've just learned today into one final demonstration where we create a nice loud explosion. So inside this very old, dirty Gatorade bottle, I'm going to add just some plain water. All right, so water just like that first demonstration with the Alka-Seltzer. Water into there. Okay, then we need to create a fuel. And the fuel that we're going to create is through the use of these tiny black rocks that we have right here, okay? When we add these rocks to the water, they're going to bubble and they're going to fizz just like the Alka-Seltzer, except the gas in this case is highly flammable. Highly flammable. So that means that it's going to burn very, very well. So just a few of these rocks should do it. They're going to create the gas inside there. Now, remember what we need. We need a fuel. And so that's the gas that's going to be created. Where are we going to get heat? We're going to get heat with the use of this device right here. When I click this button, a tiny spark forms on the end of these wires. So you might have seen one of these on your grill, right? If you press the button, it ignites the fuel that comes out of your grill. So a tiny spark on the end of there. Do you think that spark is cold or hot? Yeah, it's going to be very, very hot. Just enough heat to ignite the fuel inside there. And then we need oxygen, right? Where do we get the oxygen again? From the air. So there's air inside this bottle as well. We're going to create some gas, mix it with the oxygen, ignite it with our spark igniter here. Now, just like the first demonstration that we did with the bottle that blew out the flames, that's called our whoosh bottle, and everything just came out the top, didn't it? What if we contained all of that, like the first demonstration with the Alka-Seltzer? What if I plugged the top of this Gatorade bottle with a bandana? All right, it would increase the rate of reaction so that all of that energy would be released very, very rapidly, and we should end up with a pretty loud bang. You guys ready? Okay, I must reiterate that please do not try any of these things at home. These can be very, very dangerous, and I do not want anyone getting hurt. If you would like to see these things again, I would invite you to come down to the Science Center or any science center that you might live around, or ask a science teacher at your school. Okay? Sound good? All right, so I'm going to add these, and oh, you know what? One more thing. Instead of counting down 3, 2, 1, how about we count down with our 3 ingredients? So we say fuel, heat, oxygen, and then we go bang. Does that sound good? Let's practice one time. Here we go. Fuel, heat, oxygen, and then we'll go bang. Okay, are you guys ready? So I want to thank you all so much, and I want to once again thank the Community Foundation for sponsoring these programs. We have our gas being created inside there just like so. I'm going to put on my ear protectors, and if you guys would also cover your ears. Here we go. Fuel, heat, oxygen. Thank you guys. Thank you guys so much. Thank you to the library. Thank you to the Community Foundation as well.